Hi, good morning, everyone. Welcome back to the third day. Just a couple of things. We will have a workshop photo at 10:50. We'll gather together around the globe and we have something there. And the other things, so in addition to Mladen and myself, we have a third co-organizer of this workshop, Ellen Eischen from the University of Oregon, who sends her regards. She can't be here because she has something to organize in a couple of weeks, and all the Lisas of her department left the math department. So it's just imagine everything that's all these checking people in and organizing trips and everything is gone. But hello from Oregon as well. And now let's get started.
So let me pick it up from where I left off yesterday. We were talking about these kind of sheaf homologies. This one notation. This is a locally symmetric space. That's a sheaf on the space, given attached to an algebraic finite dimensional irreducible representation of the group, the algebraic group G with highest weight mu. Introduced. So what I want to do today is talk a little more about what one does with these cohomology groups, which there is a certain standard isomorphism of this with a different looking cohomology group. So before I do that, let me just go back and review a little bit of homological algebra. So because this was purely sheaf theoretically defined. And that itself, if this AF is small enough, and let's say I work with one connected component, then this was related to group cohomology. So that's one side of the story. The other side of the story relates this to what's called Lie algebra or relative Lie algebra cohomology. How does this work? So suppose I have I'm going to use notation compatible with my global notation. So G infinity, this math frac G infinity, this is the Lie algebra of the input GR. Deliberately not really writing down what G is. The simplest situation that we want to talk about is GL2 over Q, or I can work with GLN or a number field, or if I want to work with a Q group, I restrict my scalars from F to Q of GLN or the number field, or just any connected reductive group over a number field. Any context group is fine. And K infinity, it's essentially maximum compact with a bit of center. That's of course a kind of vague qualification of maximal compact, but you saw what I did last time. Back on a bit of this to make my space finite volume, and then I'll take its connected component. The circle or top is always the connected component of that. And suppose V is a GK module. So it's a vector space on which the Lie algebra acts, on which this compact group acts, and the actions are compatible. So if I differentiate the action of the compact group, that is the algebra of G infinity, and that there must be some compatibility there. And there is also an adjoint action of the group on the Lie algebra, and there's some various compatibilities that you want to ask for. But where both it's a vector space on which these two act compatibly. Then to this you attach this is this relative Lie algebra homology. What is this? This is the homology of a certain complex. And what is this complex? So CQ, G infinity, K infinity. is we look at K equivariant maps from which Q of the Lie algebra G mod the Lie algebra of K. And it's always a good idea to work here in this situation with a connected component of the identity, because then you can, using this complex, it's easy to see that there is an action of K infinity mod K infinity circle on these homology groups. And that's very useful baggage to carry through any analysis with this kind of homology. So once I have this, I'll come back to my second review in a minute. Here then, this sheet homology is related to. Let me just work with my representation space is over a complex. This finite dimensional representation is over a complex vector space. Then this, there's a basic fact that this is isomorphic to the relatively algebra homology with coefficients in the space of smooth function from GA mod GQ. And since I have some level structure, we take care of invariance of that and so this rectification. So this was actually have raised this is chief homology, and this side is relatively algebra. This kind of an isomorphism goes by the name Matsushima Murakami type. On the first day, I told you, that these kind of workshops have happened, and they have the virtues and what kind of point of view to take. In any case, when I was a student, I went to this workshop in Edinburgh back in '96 or 1901, and Bogan gave this very beautiful lectures, and his notes is a very good window to understanding this isomorphism. Actually, it looks complicated, but when you start digging into what really is sheet homology, take some resolution, work with differential forms, and it feels very natural to go from here. The complex which computes this homology, you kind of stare at it, interpret it, and it visually becomes this complex. Well, what is I didn't tell you the D map. This is just like exterior differentiation. Which you might be familiar with from the picture. This is essentially this way of automorphic forms. I told you, bare bone was an automorphic form with a function on GA with some GQ invariants, and all kinds of function spaces, and we would get into which space am I exactly working with, and so on. But nevertheless, here is automorphic forms. There is a deep theorem of Borel which says that the inclusion of the space of smooth cut forms and invariants are like here. This space of cut forms sits inside the space of automorphic forms. This inclusion induces an inclusion in homology. There's a theorem of Borel. Oh, by the way, a good reference for this kind of stuff is if you want to look at Borel and Borel's work. And so there is some subspace inside this sheet theoretically defined homology group, which maps isomorphically to the homology of the space of cut forms. And that, by definition, is Customary homology. This sits here. It's the subspace which is mapped isomorphically to this. in terms of homology classes, this is represented by differential forms using cusp forms. So other ways to organize your thoughts with this, the space of cusp forms, I drew these theorems at you yesterday, this general facts, the space of cusp forms decomposes as a direct sum of cuspidal automorphic representations. And so, and these homology groups compute with this direct sum. So this then becomes isomorphic to the sum running over pi. And maybe kf invariance with multiplicities. Remember, this multiplicity is one if I'm working with DLN. This GK homology is sort of massaging the representation only at infinity. This is saying only the action of the group at infinity. So if I decompose my representation, global representation pi as the representation at infinity and everything else, this is really affecting the representation at infinity. So I can take that out, take the remaining part. And kf. I want to explain something about this the GK homology of pi infinity in the easiest non-trivial example of GL2 over Q globally and GL2R at infinity. So that's my going back to this review. Before I can do that, let me remind you of something else in homological algebra. Something about X groups. X groups. So let me just go to the category of modules over a ring. I can look at X in the category of R modules between two modules M and N. And there is a result going back to Unita of this Unita extensions, which relates this X group to, is the same as isomorphic. You set up all exact sequences X from M to N is exact sequences of length. Let's say if I do X cube of length Q from N to N. Mod and obvious equivalence. So two such sequences will be considered equal, and put them one next to the other, and there's an arrow. The equalities from M and N, and arrows from A1, A2, any AJ to any of the features. A good reference for this. In fact, most references will start talking about this, and then they'll refer to Maclain's homology. The whole classic. So now where are X groups here? This relative algebra homology, which is slightly more is like essentially like the algebra homology, which is essentially like group homology, and that is some X group. So likewise, this is also extensions in the right category modules or GK modules between the trivial representation. So this is I can't really say it's an exercise, but once you get into this, if you look at Burns Waller, you can see this. The resolution of the trivial representation is built from these wedge Q's G mod K. And then you see the relation that this the algebra homology is kind of extreme.
Sorry, Raghuram,
Yeah.
can you say what CG infinity came to?
The appropriate category of GK module. So
Okay.
category of
So some kind of GK infinity K infinity model.
yeah, atoms is one.
Okay.
And you have to make all the relevant observations that there's an Abelian category of injectives and so on, and you can play this formula to create in that category. And you see where I'm going. Yesterday I put down a certain short exact sequence for GL to R. Recall from the study that if I have two integers A and B, A is equal to B, and this is my highest grade mu, then I had a certain induced representation built out of this A and B, which quotients down to M mu. Maybe let's go for complex numbers. M mu is the A minus B at symmetric of the standard representation. This that's somehow determined. And the sub at not by D. This short exact sequence doesn't split. And by the way, in Unida extensions, the trivial class here corresponds to some kind of split exact sequence. So here, if it's just x1, the trivial element is the direct sum of the modules it ends. Yeah.
Start dual somewhere.
Not yet. It's going to come in a minute. So this short exact sequence does not split as this was G to R SO2 positive units. So this gives rise to an element of x1 in the right G. This category G to R SO2 the category of modules between N mu and D mu. And then it's really an exercise to see that this finite dimensional module can be pushed across the comma sign. Realize this is the same as x1 between the trivial representation and N mu dual and so. So back to this example of if I have a weight K cusp form for gamma naught n and some character, and to this I take the associated coupled automorphic representation. I've deliberately changed my notation from F to F phi. You'll see later today why I'm doing this. And then part of this dictionary was that this representation of infinity is a discrete series representation, which I think I denoted dk minus 1. This is d mu k. Mu k is k minus 2 by 2 and minus k minus 2 by 2. Assume k is even. If k is odd, I have to tensor it by absolute value to the half, and then it becomes formless. So there's a little bit of I don't want to get into that take part here. So I take k even, and then I know the representation at infinity is on the most this dk minus 1. And so keep everything on one board. That my board will get the edges go here. So back to this beautiful example. So you see that H1 of GM are SO2 of equivalence of representation at infinity associated with cusp form of weight K twisted by M. This weight, the corresponding representation is going to be self-dual, right? Move it by, if I take you hit it by the while loop element of longest length and see in a minus sign, it's still the same weight. So this for N mu, okay, check. So I don't have to worry so much about the dualizing. So I get a class. This, in fact, is two-dimensional, and both the trivial character and the sign character appears. So as a total mod SO2. one place to see these details is there's an article I wrote with my student Naomi, my then student, which appeared, I'd like to say 2011. We have written only one paper, so in the Journal of Ramanujan Math Society, where this, as well as the corresponding story for the good model, comes out. So this is the sort of ingredient which goes into this part. And then the finite part of the representation is the outside. Together, they add up to give me cuspidal cohomology. So much is what I wanted to talk about as far as homology of arithmetic groups is concerned.
So just to summarize that,
Yeah,
this cuspidal cohomology breaks up into a direct sum over automorphic representation.
cuspidal automorphic.
Yeah, of some two-dimensional vector space tensored with those invariants.
Right.
That's okay.
For
GL2.
for GL2.
Yeah.
So let me just write that down. So in particular, for G equals GL2 for Q, and mu is mu K, H1 cusp of a locally symmetric space for GL2, and let me say K1N. So I don't have to worry about that too much. And mu K C is the direct sum over representations pi is pi sk gamma 1n primitive h1 of the relevant G infinity K infinity circle of dk minus 1 and so on. So this dk minus 1 is pi infinity tensor. Finite part invariants under K. Sorry? No, yeah,
Because you don't invariance. If you just erase primitive, is correct.
no, I would, otherwise you don't have irreducibility of the cuspidal automorphic. Would not even talk about the cuspidal automorphic.
Just say over all new forms. Because this invariant is non-zero, you can only if the level is small step.
If I didn't, yeah, I'm a little confused myself at the moment. If I didn't have primitive, the pi is not even defined. Not an irreducible. If I take the sum of two cusp forms of it,
Then just erase pi.
yeah, I just wanted to relate. I should have. I'm just doing this real time. I had to prepare to write this down.
If you just erase pi, it's correct.
If I just erase pi,
If you is correct, yeah. But you post infinity type.
something like this is true. Fix this.
No, but it's written above, I guess, yes. You just wanted to make it precise, I guess.
Yeah. Yeah.
The last thing, the fact that you know that there are only two possible extensions between the mu or dmu, or it will be otherwise.
No. So one has to put, this fact is not obvious from what it is said here. There is some little more work to do. So the work to do is goes here. You look at wedge 1 of G mod K, so that's GL2 mod SO2 and reals. And you think of it as, as an O2, SO2 module, see what characters appear. And what characters appear, what are the K types of D mu and N mu. And you have to do a little exercise, and then you see that, after doing that exercise, one can deduce this. This was simply to say that, well, okay, there is an X1 class, and not trivial X1. Given that it's, once we know that this doesn't still.
If you really want to put this prime, just put n prime with n prime dividing n, and that's correct.
Okay, so now I want to get into talking about the functions. A rapid introduction to Hacker theory. So if I take a phi, which is the holomorphic form of some weight, some level, some negatives. By the way, sometimes I go with gamma naught n, sometimes I go with gamma 1n. I don't know if I mentioned this, this is a key exercise. That if I take the space of weight k corresponds for gamma 1n, then this is the sum. I don't know, did I put this down yesterday? There's a sum over Dirichlet characters I mod n of sk gamma naught n. So this is an easy conclusion. There's an action of, I told you that this this is normal in this, and then you put that. So what Hecker did, he looked at this integral, phi of I y to the s minus 1 dy from 0 to infinity. So let me compute this integral. And let's say this phi has a Fourier expansion summation k and q then I and z and then 1 to infinity. So this is the integral from 0 to infinity. Phi, I use this Fourier expansion, summing n going from 1 to infinity of a n. If I put z as iy, this becomes e to the minus 2 pi n y, y to the s minus 1 dy. Of course, you see an integral and a summation, you know, you have to interchange them. You have to justify how everything works. So I go ahead and interchange. The a n comes out. Then I have the integral 0 to infinity e to the minus 2 pi n y, y to the s minus 1 dy. And it's better to write this as y to the s and dy by y. And if I make the substitution, put 2 pi and y as t, then this becomes summation n going from 1 to infinity of a n 0 to infinity e to the minus t, y becomes t by 2 pi n. So t to the s and 2 pi n to the s, I pull it out. And dy by y becomes dt by t, it's the invariant measure. And then you see that this is really the gamma function. So if I go here, this becomes, I pull the gamma function out, outside the summation, I pull this 2 pi to the s out, the minus s, gamma s, and then what remains is, I'm going from 1 to infinity of a n. It's a very nice calculation. This is the finite part of the L function, and this is the completed L function. So let me denote this. This is the finite part of the L function. And to denote finite part, I want an L sub f. And this is the completed L function. I denote Ls. And it's, since I wanted the subscript f, is why I changed my modular form from f to the phi. And so the basic analytic story, you have to put the analytic story in place. You got a infinite summation, you have to worry about convergence. Convergence in a half plane. Convergence for real particles. You know, you can make it precise using even the trivial bound for the Fourier coefficients. We go ahead to the k by 2. So if s real part of s is larger than 1 plus k by 2, then you're good. It admits an analytic continuation. For all of us. There is a technical thing about bounded and vertical strips, and finally satisfies the functional equation of this kind. That I'm also going to slightly jazz up my L function by bringing in a twisting character. So phi r. So I'm going to also change my Lagrange equals from chi to omega. That omega didn't play any role so far. And chi is going to be any direction. And I'm going to denote the finite part of the L function of phi twisted by chi by definition. It's coming a n, the Fourier coefficient of phi. times chi n by n plus. So for the twisted L functions, you have this functional equation Ls by I is, I wanted to look up Shimura before when I prepared and I forgot to look it up. There's a precise epsilon factor, harmless exponential here, times the dual side is Lk minus S, phi hit by the Eigenvalue 0 minus 1 and 0. Okay. That's that. If I take phi is pyramidal, this guy is also pyramidal, and its representation is the dual of the representation attached to phi. For the precise form, look up Shimura. I seem to recall just this part in Gilbert's book, there was some detail which was bothering me. So should we say to go? So now, having introduced the L function, let me start talking about arithmetic aspects. And for that, you see this the gamma factor on either side of the function equation that starts playing a role. Here's the definition. I'm going to denote this L infinity as phi. The gamma factor for the infinite part here is also the same. Happens to be the same. Definition, an integer is said to be critical for the L function of phi twisted by chi if the gamma factors on either side of the function equation, so L infinity s phi chi and L infinity of k minus s. I'm going to denote this as phi check. Inverse are regular, meaning no poles. So that's finite. Yes. Then it's an exercise to work out what is the critical set. So M is critical. Basically, it will come down to if and only if gamma M and gamma k minus m are finite. And then you know the poles of the gamma function. They are the non-positive integers, 0, minus 1, minus 2, etc. They're all simple poles. We can work it out that the critical set then, critical set for the L function of the modular form is the finite set 1, 2, 3 up to k minus. If you did this for the Riemann zeta function, right, look at the gamma factors for the Riemann zeta function and you work out the same exercise, you will see the even positive integers and the odd negative integers as a critical set. There is an infinite set for GL2 and higher GL1 typically is a finite set. Zeta 2 is pi squared by 6. Zeta 4 is pi to the 4 times the rational, that was the rational. What is the analogous statement that one can go to do for the values of this L function at these critical points? So this is the theorem going back to Manin and Shimura. Before I can state the theorem, I need some arithmetic details.
I have a question.
Yeah, go ahead.
For this exercise, what you want to show us that the finite part L function is defined everywhere,
After analytically continuing it. It's not given by the series everywhere, but then it admits an analytic.
Okay, and that analytic equation has no poles.
Yeah, it has no poles.
Okay.
The L function attached to a cusp form, and more generally for a cuspal automorphic representation of GLN, will have no poles. it has an entire, it analytically continues from entire. Are you going to talk about brackets and function and its modes? I mean, you did locally yesterday.
So, I'm going to say
Anything. This is a deep theorem, it's not obvious. Here, you could kind of get a feel for it here because this corresponds rapidly decay. And so this integral, after integrate to some finite place and then the rest of it you can make it small. Okay. So you can kind of get the analytic continuation from this integral. Am I expert can correct me? Yeah.
supposed to reflect the R2 context.
Yes. Okay, so where am I? I want to talk about humorous term. And before we can do so, I need some basic arithmetic facts. This one. Fact, theorem. I don't know historically who this theorem would go to, but in any case, I'm going to put Shimura's name here. Reference to Shimura's book. Although I'm going to put on a somewhat simplified form of the statement that if I look at the space of weight K corresponds for gamma 1n, this has a basis consisting of corresponds with Q Fourier functions. There are different ways of talking about this theorem. If I take the Q span of this basis of corresponds with Q Fourier coefficients, that the Q subspace inside the space of corresponds, and that gives me a rational structure. There are other ways of talking about this. So more generally, the theorem of Raghuram, Arda, and Tuzel that the Customary cohomology for JLN admits a rational structure. So there is that statement first one has to qualify it properly, and then correct statement, and the deep theorem for GL2 over Q for modular forms of this. It looks like this.
Will it necessarily be rational at all expansions at all cusps?
Yeah. Yes, this one is actually correct. Yeah. Back to the question from the first day. So from this, here's an exercise. Maybe for effect, let me just put down what I did on this board itself. That Sk comma 1n is the sum over Dirichlet characters mod n Sk comma naught n. So if I take the weight K cusp form for gamma naught n and character omega, and say its Fourier expansion looks like summation A and Q to n. And I take sigma as a automorphism of complex numbers as a field. And you define the sigma conjugate of phi via the action of sigma on the Fourier coefficients. The sigma phi on Z by definition is summing sigma an e to the phi I Z. This is not just a random function that you can define. In fact, that's the exercise. In fact, show that sigma phi is also a weight K cusp form for gamma naught n, and the Nebentifus would be sigma composed. Omega is of course a Dirichlet character, right? So omega is a character of this kind, Z mod and Z cross, C cross, and sigma being a field automorphism gives me a homomorphism of C cross to C cross, and I compose. So this exercise, use this, and you can deduce this exercise. Now I have all the ingredients to state Shimura's theorem. Goes back to Manin for modular forms for Sn to Z. and Shimura non-generality. This theorem deserves a really clean board. If you want a reference, this is look up Shimura's paper in Mathematische Analyse. So take a cusp-form phi of weight k, level n, and character omega. Assume it's primitive. Or maybe one more exercise. I think that should be. Phi the weight k, level n, and primitive, then show that the field obtained by adjoining all the Fourier coefficients of phi. Okay, back to the theorem. Take a cusp form of weight k, level n, and character. What Shimura 1 and Shimura k is to this there exists two periods. I'll use Shimura's notation u plus or minus phi. These are called periods. In fact, the title of this paper is periods of model forms, periods of phi. Such that for any Dirichlet character chi, this is my twisting character. Any twisting character, and take any critical point, and for m in this critical set, if you look at the value of this L function, the finite part of the cusp form twisted by this character chi, and a divide by 2 pi I to the m. One of these two periods, there's a certain recipe of defining the periods and picking the right period, and the Gauss sum. Define the Gauss sum. I is a Dirichlet character, not only of modulus m, but let's say of conductor. And then the Gauss sum. It's some kind of Fourier transform of chi. It's an edited Fourier transform of chi. It's the sum of a from 1 to n. Next one, I e to the 2 pi I. This quantity is algebraic. Maybe let me try to do this algebraic. And furthermore, and for all sigma in the Galois group of q bar over q, or I can, Shimura would say odd c, but it's really, its restriction to q bar is what is relevant for any element in the Galois group of q bar over q. If I hit this L value divided by these periods, appropriate power of 2 pi I, one of these two periods, and the Gauss sum of chi, then it satisfies this beautiful reciprocity law that sigma applied to this is the corresponding quantity for the sigma conjugated objects. So sigma chi, I mean the sigma compose chi divided by 2 pi I to the m, the periods of the conjugated cusp form and the Gauss sum of the conjugated character. Which period you pick depends on the parity of m and the parity of chi. So that determines the signature. So, sorry. Yeah, well, I haven't defined the period, so it doesn't matter.
Right, but like for elliptic curve points at one, you want the plus period. Just an elliptic curve and a trivial character. Usually people take the plus period, of course.
Since I haven't even defined it, it doesn't matter.
Sure.
This is the nature of theorem on special values of the functions that people aspire to prove to get the arithmetic story started. Once you have this, then comes, in fact, the rest of the workshop is, what do you do, how can you study congruences, what is algebraic quantity, how do these algebraic quantities interpolate p-adically, and so on and so forth. Once the theorem is in place, another story picks up from there. Some people also refer to results like this as algebraicity theorems or rationality results for the special value of the functions. So, did you want me to say anything more for the p-adic functions?
Oh, no, that's perfect.
So what I want to do in 10 minutes is maybe here's the exercise. Call this equation, let's simply call this star, then show that star implies that this, to simplify my, if I call this quantity as the algebraic part, the value is, well, algebraic, all right, but it lands inside the field q phi comma chi, where this is q adjoin all the Fourier coefficients of phi, adjoin the values of chi. It lives in that number field, comes down. It's not just algebraic somewhere up there, but this is as much as we can push it. Let me keep all this on the board. We can take this off. There are different ways to prove this theorem. I would like to just show you. I can use this kind of cohomological considerations to prove the theorem of this kind. I like the German system with the ratio water.
Yeah, that's something great. So that's your about.
Okay, so one approach to proving theorems of this kind logical. Is I just put this in one sentence, and then what I want to do is just put on one diagram to organize your thoughts around that sentence. Is you see this integral, which gives me this function. You want to realize this integral, the Mellin transform, as the integral coming from point that value. That's the one sentence proof of this theorem. So you interpret. Then in transform. As integral. Coming from. We are to, what version of functional duality I'm going to use. So let me just recall for you some basic flag you might have seen in topology that if I have a M is a connected oriented manifold of dimension n, some dimension say T, then the top degree homology with compact supports of this manifold with the constant quotient C. This is isomorphic to C. And what's isomorphism? You take a differential form of degree D, you fix an orientation on the manifold and you integrate. So this is one. This,
With C. Even with C, which will be used.
yeah. So, you're getting ahead of me. So, so first you see this here, and then you realize that this actually works rationally, and in fact, integral. What not just said. So this works. Can replace C. Y. Well, in some sense, whatever you want to do, Q, QP, Z. I mean, you do it or integer, and then you can base change from there to wherever else.
Even though the formula is not going to make sense over those.
That's right. Yeah. So there is an isomorphism. Yeah. So if I take a cusp form of some level tables, and to this I take phi is the hospital automorphic representation. And I think Nader already mentioned that after you talk about Whittaker models, that a cuspidal automorphic representation has a global Whittaker model. So I'm just going to do it up to phi, and which will be a tensor product of local Whittaker models. And once again, I'll put this all the finite local spaces are put into phi f and phi infinity. I know the shape of phi infinity very well. It's basically -1. Except I'm thinking of it in its Whittaker model. That's just some model for the representation space. It's convenient to work with some functions of which you can then integrate into other things. Okay, so here is my one diagram summary of how one proves theorems of this kind. One approach. Let me start with the Whittaker model of the finite part. From this, I tensor this with a one-dimensional space. Years ago, when I was getting started on special values over functions, Hardler told me that if you want to play this game, you have to learn the art of fixing a basis for a one-dimensional vector space. And this happens many times. There's one such place. And one-dimensional, I just take a space and tensor it with C again. Except the C is not just the line complex numbers, but well, it was on this board. So this is going to be H1 of GL2, SO2 of phi infinity, except I take it in its Whittaker model, tensor with M mu K. And this was K infinity circle. I told you this is a two-dimensional space, and then you work with whichever signature that you want. That's how mine is. Let me just work with this. This is one image. And all this, I kind of go backwards. So this The GK cohomology business is only kind of doing something to the representation of utility. This finite part was untouched. So I take it inside and club it together with the vertical model of phi infinity and write this of H1 G infinity K infinity of the full global vertical model of phi instead of n. This the global vertical model, let's say, is as a module is isomorphic to the space of cusp forms, this living in the space of cusp forms. So this is isomorphic H1 space of cusp forms, realizing this representation phi is kept by this finite dimensional representation. This was one summand inside cuspal cohomology. So this goes inside H1 cusp. I beg your pardon. Now, one summand of cuspal cohomology for GL2 appropriate level structures, so K1 and right. Let me just say I'm focused with one and so it's K1 and one piece inside this big cuspal cohomology. This now there's a fact that this in fact sits inside cohomology with compact subgroups. And then in this integral, the integrand, the argument of the function in the integrand, this Iy, is really the diagonal y1 acting on I. So that gives you a hint of you take GL1, sitting inside GL2, all this map iota. This map iota induces a corresponding map at the level of symmetrical location of the spaces. I have some cohomology class here. We put it back to the GL1 by saying iota star. And this iota, the map reduces the fact that it's a proper map at the level of symmetric. So what we have to worry about some level, what exactly the level structure here, anyway, we get something like this. GL1, this locally symmetric space I'm talking about, if you just work out this basic algebraic number theory, this will be just positive rails. That's my connected oriented manifold. This is one dimension. But I got some sheep here, and then you have to assume, suppose S equals half is critical for endless pi. This is another painful aspect of normalizations in an experiment, so that I can finish it off. The critical set there were integers, but if I work in the context of representations and L functions attached to GL2, then these for GL2 they are half integers. This is just a normalization. So if I assume the center of symmetry is critical, which will correspond to an assumption there that the point k by 2, where k is even is critical, then you can actually map down to the trivial. This needs some. It's not entirely this arrow where it comes from is not entirely a triviality, but it's not hard. Constant coefficients, and then you apply quantum. And what you do is you take in the finite part. I take one particular vector here. There is W naught. If the tensor product or all the finite primes of W naught P, and the W naught P is the local mu vector, which comes from that theorem of Castleman I talked about yesterday. So you feed them together. This is the in the vertical model, the finite part of the vertical model, the function that corresponds to the holomorphic form we start with. So this is the information of phi is really embedded in all these local mu vectors. And then you chase it all along. So from here, if I go take this up and you chase here, and then you unravel what's the meaning of all these objects and arrows, and out pops and up. This you have to, some level, I'm just giving you how a certain story unfolds. And where do the periods arise? Well, this is just a complex number. And so I just want to do this game rationally. I got some class here. And then you divide this class by something, some complex number to make it rational. So then out pops a theorem of this kind. That L half pi divided by some period. And then all these cosmology you can understand what happens if I take this diagram by a Galois element and then out pops rationality. And then there's a separate theorem. So this is one. That's the behavior of these periods upon twisting by character. This is a theorem of mine in Shahidi. This is behaves like two periods you can attach depending upon plus or minus that you take for the action of O2 mod SO2. And that gets moved by the parity of pi and the rest. So this behavior of periods under twisting will account for this loss. And if you work this out, you can work it out on the nose, and then you will see this theorem on the nose. Okay, sorry for going overboard.
Make a comment which will be useful for the lecture. I mean, this second to last arrow, you can just you can just denote something like crit M. Like for any critical M, you have such an arrow, and that's kind of nice because you mentioned what needs to be critical, right? And then you go to the value at LP of M.
One of the advantages of this way of thinking is it suffices to prove a theorem about one L value for a reasonably large class of representations. Then you get all the critical values for any given representation by replacing pi by various tables. So this is really a theorem about one L value. Once I have that, I get it for all critical points and all twisting characters.
No, but what you wrote is deeper because it says that you have only two periods, even if there are 100 critical M's.
Yes, so that's also here also the only two periods. So
your periods here depend on pi, so like.
and there the period depend on pi. Okay, once you have
For phi and many M's, you have different pi's. A priori, those periods depend on the twist, unless we use this out there.
yes. So Gladden's comment is, if you look at this class of all twisted L functions for a modular form, you just need to know these two numbers. Then they capture the possibly transcendental part of the critical values of any critical value of any twisted L function of that modular form. You just need those two numbers. And then there is this conjecture of Delhi, which puts it into the motivated numbers. We won't get into that.
To start with the random W on the left, in C of any some integration of W on some group.
Yeah.
You need
It might be. You might have a linear combination of L values.
This formula like
the integral is going to happen against the GL1. Ultimately, it's the same. When Jacqueline Magnus will integrate the Whittaker function on A1.
yes,
You're changing it W. Yes, sir.
Oh, no, are you still going to do?
no,
Okay. I have some questions just to orient my.
Yes.
So in the end here in the blue, there's an L. And I just want to make sure I understand, L is your completed L function.
So here,
Is that right?
I was running out of time and I kind of, have touched a little,
So I didn't think L is the Mellon term. L is the thing that has like gamma factors at infinity in it already. That's that.
and that, and now you see the small pi is, so in my papers, sometimes you'll see capital pi and little pi, is 2 pi I to a certain number, which can be determined from this mu k. And so this is what you find out.
To orient myself, what I was wondering is in these equations with something is algebraic, there's an L finite and a 2 pi to the n.
It's all finite.
Yeah. And I just want to understand, is that 2 pi to the n the same as 2 pi in the gamma factor evaluated at s equals n? That's the same exact 2 pi.
It's the same exact.
Okay, and there's no gamma of n because gamma of n is just n factorial or n minus 1 factorial,
Right.
is that right?
That's right.
Okay,
This also, you're actually getting close to. Typically, one of these periods is a real number and the other is going to be pure imaginary, and that will.
that's why the I is.
The I, it gets, so.
And then I was also wondering if you could, there's this map iota star you wrote down, and that's some restriction map somehow from a GL2 thing to a GL1 thing.
That's right.
The GL2 thing is the upper half plane mod a gamma.
That's right.
Can you just draw a picture of what you're doing geometrically?
So here, this is an iota, and then at levels multiplications, locate multiplications, you got H mod gamma here. What is the JL1? I got the upper half plane, and I go mod gamma, it becomes something like this. And the JL1 is really like, becomes on. And so you're kind of just restricting to that.
It's a specific line, or do you get
It's the
the,
same IY.
it's the vertical axis
Yeah, so
at the origin?
that's because of this error. I'll work with this.
Thank you.
Then of course, the picture is for when gamma is to Z, otherwise it's more complicated than this. And this, in fact, I've exploited this in some other, so now I'm becoming more like a colloquial. So this is a story for GL2 cross GL1. And this gets generalized in many different directions. One direction is GLN cross GLN minus 1. Another is what Gladden and I have worked on, is GL2N and integrating against GLN cross GLN. And each time there's an embedding like this, and every single time that embedding induces a proper map, that's the theorem of Gopal Prasad. And this story gets generalized in other directions, giving you analogous theorems for higher functions. Coffee, photograph.
Well, we have coffee and then the photograph in 10 minutes.
Okay.
Can we start the next one 10 minutes late so that we get a full half hour?
Sure.
Are you okay with that? Is everyone okay with that? You're speaking.
Okay.
Yeah, yeah, I think it's better.
Okay, so then, let's still do 10:50 for the photo. Just because that's the detail thing.
Yeah.
But we'll start at 11:10.
Yeah. that- So Raghuram, I had a question that wasn't meant to disorient everything about the critical values. Yeah. I mean, I know the story of the critical values. I don't know how to do this process. Finite set.
Once you put the pi infinities in
And it's just the shape of various input factors. But is there something intrinsic that makes critical values? Finite? It's just coincidence.
Almost always the case that the infinite set happens only for GL1. All
Okay.
higher GLs.
Yeah, I mean, in the p-adic story, you're often told, for instance, that although it looks like a finite set here,